Okay, so we're going to talk about Dijkstra's algorithm today and Prin's algorithm as well. I was going to do a Visual Basic program on it, but I got a little stuck. Oh, damn it. I got a little stuck in doing it, and so I decided that maybe that might be a fun way. It might be a fun addition to my normal projects. So we'll see. We'll play it by ear. So what we're going to do is we're going to initialize a graph with vertex A and no edges at all. Okay, so in other words, you've got a graph like this one here, but what we're going to do is, in essence, start building a graph, and we're going to start building it from vertex A, if you will. Okay, and we're going to start adding vertices and edges as we go. Okay, and what we're going to do is we're going to go until we've collected every single vertex, and we're going to keep adding edges to our set of edges. Here's our set of edges. We're going to keep going until we've added to them. Okay. Now the big difference between Dijkstra and Kruskal made decisions based on the immediacy of the situation. So for instance, here I am, I'm going to choose only the cheapest links, always perfectly, go, great, whatever. Dijkstra says, listen, we're going to start from this part A, okay, and we're going to branch out from there, and we're going to be looking at not just the shortest pieces, but the shortest total links to those places as we build it. Okay, so you can set up a table. I like this kind of a table. This is kind of how I was taught it back in the day. But you can do it a couple of different ways. So A's distance from itself is 0. And then everybody else, we're just going to say right now, is infinity. It doesn't really make any difference, because what we're going to do is we're going to keep trying to improve that distance. We're going to keep trying to improve that distance as we go along. Okay, so we're going to come up here. So from A to B, clearly we can go there because it's connected. We can go to A to C, and we can go A to D. Now, the distance from A to itself is 0. So 0 plus 10 units is what it takes to get to B. All right, so A to B is 10. I'm going to probably jot that down. I had to start this video over, so don't pay attention to that. So from A to B is 10. From A to C is 5. And from A to D is 16. Oops. So those, obviously the smaller of those is the one we're going to keep. So I'm going to take my pen here, this nice pretty green one, and I'm going to highlight this. So I've added that edge to my graph, you see. Okay. And so in my chart, what I'm going to do is, since 5 units is less than infinity, I'm going to replace this with 5. Okay. And where did I come from to get there? Well, I came from A to get to C. So far, if I'm building this, I could actually do this and draw it down here. But what I'm actually probably going to do is just highlight up here on my other graph. Okay, I think the highlighting, in my mind, works better. Okay. Now, let's talk about B. How many ways could we get to B that really make sense? I mean, clearly you could go A to D to H to F, then back around. And that's weird, and we'll worry about those. But we could always see, can we improve? And we'll talk more about that later. But in reality, no, we can't do it any better than what we could have, which would be A to B, which is 10. 10, and that is from A. So we will be using this edge. Boom, right there. Okay, nice. Well, let's talk about D. It's pretty clear here that the closest path to D is just to come from here to here. Yes, you could go to C to E and back to D, and we'll talk more about, we'll compare those later on, but that is not the cheapest way, obviously. It ain't going to work. Okay. And so it is pretty straightforward that that's what we're going to end up doing. And so that is 16 right here. Boom. Nice. Now let's think about this. To get to E, really there's 3 paths to choose from. You could go A to B to E, A to C to E, or A to D to E. Those are your real choices, am I right? So this would be 19, 24, and 25. 19 is the cheapest way to get to E. And that came from B. And so again, I'm going to add that edge in by using the highlighter. Nice. Sweet. Awesome. Now we're going to go ahead and look at F, but I'm going to talk about this here, right here. I'm at E. Notice if I'm at E right here, I could go back to D. Are you with me? That would be 19 plus 9 is 28. I'm sorry, 28's bigger than 16, so I wouldn't use this side. I also wouldn't come up the middle. That's just crazy as well. Okay, so that's not to worry about. Now we're talking about F now. So let's talk about good old F over here. Now F, okay, how can you get to F? Okay, well, you can go from E or you can go from B, yes? So let's think about this for a minute. So if I did A to B to F, A to B to F is a total of 28. A to B to E to F is 33. Oh my. Well, see, in this case then, I want to use that top line. Like so. Okay. Oh, shoot. And there it is. And so then, now by the way, you notice that Kruskal, or his cheapest link algorithm, would have taken the 14 at that point. Okay. Now, let's come down here. So that is to F. We are going to join that from B. And how far was it total? It was a distance of 28. Again, that is from the initial. We always come from the initial. Okay. Now, again, had you gone on the cheapest link, Kruskal's, you would have come down to here. But what happens is this. Kruskal is always talking about the shortest total tree, period. Dijkstra is trying to find the shortest paths, that's true, but of the total distances from a starting position, a hub, if you will, out to all the branches. So it's the shortest distance from the hub, not the shortest total combined. I have to go on the whole tree sort of situation. Okay. Let's keep going, shall we? G. Okay. Now, what's the closest way to get to G? Okay. Well, I could go clearly A to D to G, or I could go A to D to E to G, or I could go A to C to E to G, or I could go A to B to E to G. Okay. Here we go. So this is 25 here. Okay. Here we have 19 plus 8 is 37. Oh, I'm sorry. That's this one down here. A to D. Wait, didn't do that right. Let me back up. A to D to G is 27. A to D to E to G is 27, and 16 is 39. A to C to E to G is 37, 42. Okay, this looks to be the shortest. Ergo, I'll be using that 11. And that is 27. So that's for G. So G, I'm going to come down here, grab my pen. And that came from D. All right. And now all I have left to do is H. And so let's try this. How can I really get to H? Okay, well, let's just leave these here because, of course, I could get there from G, right? So let's think about this. I could get there from G. So clearly I could go from here to G. Okay, that would add 22 to whatever I had. Darn it, I wish I had just paid attention. That was 27 and 22 is 49, I believe. A to D is 25, 43, 65. AC is 24, 42, 64. A to B, 19, 37, 69. Okay, so that takes care of all the G's, okay? I could have gone A to D to H as well, which would be 26 and 16 is 42. I could have also come from F, so that would be, again, a variety of ways, but we know that A to B to F was the shortest way to get to F. That's 18 plus 17, or 28 plus 17 is 45. That would be A to B to F to H. Therefore, this is the best. That's 42. And that is, it comes from, oh, damn it, D comes from D, sorry. Comes from D, okay? And if I'm filling this in, there she goes. And that is how I would connect it. Remember the difference here between Kruskal's algorithm, which is just take the shortest one every single time, and this one, which is where you're taking the shortest path from the central hub. That's the biggest difference in this guy. What you will notice when you're done is that in essence, A is my hub, and everything branches out from there. Okay, that is what Dijkstra does. Okay. Now, clearly this is a for next loop sort of a situation in that I'm going to keep adding edges and vertices until I run out of edges. Okay, I'm going to do comparisons. If this new distance is less than the previous distance, then replace it. If not, next, sort of things. There's nothing wrong with this algorithm in terms of like doing it by hand, but I find that when I do it, it always feels odd to me. And the reason I think it feels odd to me is because the whole premise of it is always couched in it's a program. It's written in it's almost even written as if it was just always in a programming language, and so it's kind of neat. Interestingly enough, of course, if you look at it, it's all about data structures and stuff, and how this stuff and the graphs and things like this. So it's always going to be kind of set up like that, and so it'll read like that every time. And to me, I always feel weird and awkward when I look at the algorithm. It always looks odd to me because I feel like I'm reading something that's not meant for me as a human. So I don't know. That's just kind of my thoughts on the matter, I guess. Let's see here. There's my socks. That's cute. All right. I was going to take a picture of Prim's algorithm. We're going to walk through this as well. Maybe turn it like so. Nice. And you go away. No one likes you. And click on the doodah here. And the pictures. Camera roll. There it goes. Cool. Is that the one I want? Yep. And that one. And spin it. Alright. I'm going to pause you for just a second. Okay, so Prim's slightly different. You'll think it's very similar to kruskal, but it's a little different. They all are similar. Again, if they were perfect, they'd be called a theorem. They always work. These are just different ways of going about it. So, yeah. Clearly, I don't need these duplicated edges here. All right, so choose the smallest one to keep. All right. The parallel edges there. If you ever had a loop, for instance, we'd get rid of that as well. Apparently, I forgot to label one. I think I got them all now. Holy mackerel. So what we're going to do, just like before, we are going to get out our pen here. Prim's a little easier in terms of explaining, I think, than the other one, than Dijkstra. It's not bad. Dijkstra's not bad, but I think it's easier to explain. And so it's again, but I think it'd be harder to program. I think it would be. I don't know. So here's the game. From A, I can get to C, to G, to E, or to B. So which of those is the shortest? Looks like A to E is the shortest. Nice. Okay. Now, when I look at this, I think to myself, all right, so from E, who can I see? Okay. Well, so far now I can see 19, 10, and 18. That's true. But I remember I have been at A, so I'm always going to consider the vertices that I've been to. So I also have 7 or 17. So let's go that again. 7 to 7, 17, 7. I can do 10, 19, or 18 because those are all the ones that I can see from my 2 vertices that I've chosen thus far. So 7 is the next smallest. Okay. Now so now I've gone to 3 vertices. Okay. So from A I can still see B. Okay. From G I can also see B. I can see E. I can see F. E I can see still to H and to D. Right. Those are the ones I need to consider. So it's 19, 18, 21, 10, or 20, or 17. 10, you're like, oh, 10's the next smallest. Ooh, not so fast, Haas. That gives us a circuit, and I can't have that. So it's 17, 19, 18, 21, or 20. 17 is now the smallest. Okay. Now, look who I have not connected to. I'm not connected to D or C or H or F. Cool. So I need to look, I need to consider to go from G, from E, from E, and from B. Now, what I can do, and I think this is helpful, is to get rid of the roads that I'm not going to use. I know I'm not going to use those guys. Okay. I think it's quite clear now when I look at it. All right, cool. So I'm comparing 21, 18, 19, and 11 and 16. 11 is the one I'm going to choose. Now that I've connected to D, like so, well, you're not going to go back to E because that, again, would create a circuit. Not going to do it. Wouldn't be prudent. Okay. And now I'm comparing from B, like leaving B, leaving D, leaving E, and leaving G. So it's 21, it's 8. Oh, you go away. 21, 18, 14, or 16. 14 is the next smallest, which means I'm getting rid of that side there. And now here we go. We can go from C, from E, and from G. So 21, 18, and 12. That's the one I'm going to choose. Okay. I don't need this 18 anymore, and obviously the reason for that is because I would create a circuit. So now I'm down to two edges that need to connect to F. Clearly this is the shortest path. Boom. Voila, Prim's algorithm. Okay, so again, Dijkstra always combines the total lengths from a starting location. Prim's is very similar to nearest neighbor algorithm that we did before when we did Hamiltonian circuits. The difference being is we don't have to make a circuit where I go from A to B to D to E to F to back around. Okay, so it's as if it's nearest neighbor from each place that we've already been to. Okay, I'm going to do another one of these real quick and see where we go from there. On this next one, I'm going to do it two ways. And I'm going to do it all three ways. I'm going to use all three algorithms on it just for a good time. So here it is. This is a picture that's, this is a picture that's very similar to in your book, although I'm not going to label it VO, V1, V2 because that creeps me out. I'm just going to call it A, B, C, D, and E. I just find that that's less confusing to me. I get confused easily. Uh-huh. 12, 20, 19. One would already know you're going to use 19, right? Because to get out to this fella, you're going to have to use the smaller of those two, right? 18 and 5. Okay. That is if you're using prims, of course. 2, 15, 7, 10, 4, 8, and 13. Okay, I'm going to go ahead and copy this guy and keep it. Well, I think I'll make 3 pictures for it. How about that? Where's my darn snipping tool? Snip. Oh, fart. Oh, fiddle faddle. Snipping tool. There you go. Give it to me. Give it to me, you hippie. All right. Oh, there. Snipping tool. There we go. Cool. New. Nice. That's hot. Control C. Copy. All right. Let's paste it in here. Paste. And let's paste it on another page too. And we'll do 3 examples of the same thing, shall we? All right, here we go. So let's do kruskal this time. Kruskal. And I'm gonna go ahead and label these as A, B, C, D, E, F, G, and H. Okay, so kruskal says, hey, let's go in. I'm gonna grab the highlighter again. Let's go in. We're gonna use the shortest ones each time. So boom. Gonna use him. Gonna use him. Cool. 4 is the next shortest. Awesome. Okay. 5. Oh, Oh, dang it. It's 2, 4. I'm sorry. I don't count well. 2, then 4, then 5. How about that? Yay. Okay, 7's next. Not so fast. That makes a circuit. We don't want that. Okay, who's next? 8. Cool. Done. All right. Who's next biggest after 8? 10. Cool. Done. Okay. Now, who do we need to connect to? Well, we need to get down to D eventually. Yes. And we need to get to H, obviously. So let's just keep going. That was 10. 12 will make a circuit. 13. Sweet. 15. No. 15, I don't need it. Can make a circuit. 18. No. Makes a circuit. 19. Done. Okay. That's kruskal. Okay. Slicker and snot. All right. Next. Let's do prim, shall we? Prim. All right. Oops. Need your pen, stupid. Okay, so on prim's algorithm, okay, I'm going to start at one of them. Oh, I didn't pay attention to who I labeled who. D, E, F, G, H. All right, cool. So let's start A, just for a good time. So on prim, okay, if I start at A, I could go to A, on the 4 or the 12. Well, I want this one. Cool. Now remember, I have been at A and I've been at B. So I can go on the 12, the 10, or the 8. Well, the 8 is the cheaper, so I'm going to go there. Now I could go on the 12, the 10, or the 13. 10's the cheapest. Okay. Now I could go on the 12, the 7, the 2, the 15, or the 13. 2 is the next. Okay. Now I could go the 12, the 7, the 5, the 18, the 15, or the 13. Okay. I believe 5 is the next biggest. Yes. Now I could go. I don't need to go on the 12 anymore. You with me? Because that would make a circuit. So I could go on the 20, the 18, the 15, the 13. Those are my choices. 13 it is. Okay. And now it's simply a matter of going, well, I can't go from the 18 here or the 15 because those make circuits, obviously. So now it's the 20 or the 19. Voila, done. Now, how does that compare to kruskal? Oh my gosh, it's literally the same on this one. Okay. Will they always be the same? No, they will not always be the same. Some of them will be different. And so just be aware of that. They're algorithms. None of them are going there. You will make a lemon meringue pie from the recipe. It doesn't guarantee that it's the best lemon meringue pie. Oops. Yeah, but you will, in theory, make a lemon meringue pie if you follow the recipe. E, F, G, H. This one will be Dijkstra's. Okay. Dijkstra's algorithm. Okay. So, again, if it's me, I lay it out like a foo. A, B, C, D, E, F, G, H. 0, distance from A to A, obviously. Infinity on all the rest for right now. And then, from what vertex. I like to keep track of that as I go. And then, of course, your vertex. Okay, starting at A, I can go to A to G, or I can go A to B. Okay, well, A to B is the smallest. So A to B is 4 units, and that is, I came from A. Okay, now let's keep going here. I'm going to minimize this just a slight bit so I get out my pen and have it at the ready. So I'm going to use this fella. Okay, now get my black pen back. Now, okay, cool. So how can I get to C? Okay, well, I could go A to B to C, which is 12, obviously. Or I could go some convoluted way to get there. Every other convoluted way will be more than 12. It's pretty straightforward. So we're definitely going to use that one. Okay. Now, how do I get to D? Okay. Now, I think you're going to see on this one is I could go 12 to 5 to 18, but that's 23, it's 35. Or I could go 25. Or I could go for 14, 25, 29. So it's pretty clear A, B, C, D. Oops. Yeah, just a minute, I gotta change something here. So A, B, C, D is going to be our shortest path to get there, and that will be 25. Cool. Now, how many ways can I get to E? Well, I could go 12, and then 7 is 19. I could go 4 and 10 is 14. I could go down and around and back up around a corner. That's ridiculous. So really it's between 14 and 19, obviously. 14 wins. So 14 goes there. And that came from B. And let me get my pen out. Boom. Like, Jay, I think it's going to be the same one. It might be, or it might not be, sir, ma'am, person. I don't know. Whoever said that, I wasn't paying attention. It's quite possible that you are correct. Hey, listen, to get to F, I could go 12 and 5 is 17. Are you with me? I could go 14 and 2 is 16. Interesting. I could go 19 and 2 is 21. That seems weird. I could come all the way down and around Robin Hood's barn. That's ludicrous. So it's pretty clear to A to G. So I could have, really it's between A to G to F, which is 17, or A to B to E to F, which is 16. So 16, it came from E, and you're like, oh, it's going to be the exact same one again. It is this time, yeah. Had this been like one number smaller there, perhaps, like, or maybe had this been like 3 or 4, had this been like a 3 here or something, then I perhaps would have gone this direction instead. Okay. Now, would that have changed on the way my kruskal turned out? Perhaps, I don't know. To get to G, it's pretty clear, I think, just staring at it. The clearest way to get there is to go from A to G, obviously. But that doesn't mean you couldn't do this. It's 21 to get to there, or it's 14, 16, 21 to get to there. But obviously 12 is the one that we're going to want to use from A. Okay? And then there you go. Now, the last one is the one that's going to be a little funky, I think. Okay? And so let's just look at this guy here. Oops, I need my pen. Okay? Now, the last one's going to be a little funky. How many ways can you get to H? Let's see. A lot. And so you could go around the corner. That's 12, 25, 44. True. You could go 32. That's true. You could do any number of weird crisscrosses to get there. It's quite clear that it's going to be either the top route or the long way around the Robin Hood's barn route. It looks like this route here is going to be our best route. So 32. There it is. And look what you got, friends. That ended up giving you what? That ended up giving you the Dijkstra's path, which is a little bit different than the one we just did on the other page. Okay? So if you go look at the other ones, you will see that kruskal and Prim gave us that one, but Dijkstra gave us this one. Okay? Now, in terms of total distance of the, like, so this is railroads that you have to lay, 32, 34, 44, 48, 56. And on this one, it's 12, 22, 24, 29, 48, 61, I think, on this guy. Okay? And so just be aware of that. Kruskal and Prim are both, to some degree, what they're called greedy algorithms. It's what's best for me right now, okay, instead of overlooking at the overall arching picture. That's why Dijkstra's, in this case in particular, comes out better. So there you go. So those of you software people, I'm probably going to extend the project to include a graphing portion, or not graphing portion, a programming portion. Details will follow. That's just something that I've been thinking about doing. So here you go.